Hi, I thought I'd talk a little bit about this game show. It was called, well, it's still on actually. It's called Let's Make a Deal, and the host was Monty Hall. That's why this is called the Monty Hall problem. But in the words above, actually, this is page 34 in the notes. I'm trying to explain what the Monty Hall problem is, but I'll actually show you with this example. You have three doors. And what would happen is a contestant would choose one of these doors, and behind one of them is a great, great prize. Okay, whatever, big vacation. And the other two are pretty crappy prizes, like maybe tuna fish or goat, or a goat. Maybe you want a goat, I don't know, but a goat or something like that. So you would choose a door. So it's the end of the game. Monty Hall says, okay, what door do you like to have the valuable prize? So maybe you say, okay, big check mark, I want door one. And what he's going to do then is there's two remaining doors, and there's got to be crap behind one of those. So he is going to, I'm going to show it like this, he's going to open one of these doors and reveal to you a crappy prize. And now you're down to two choices, and he says, do you want to keep the door or switch your door? And remember, you want to win the prize. So does it not matter? Should you switch? Should you stay the same? And so this is like a really big problem, a big in probability. I mean, everybody has heard of this. No. Um, so that's why I thought I should introduce it. It's very popular, and that woman, Marilyn von Savant, she's supposed to be the smartest woman or whatever, with the highest IQ. People write in and talk about this problem, and probability people, math people, everybody just drives them crazy. So yeah, the first quarter I taught this, people were like, no, no, this door. So it is a paradox, and it's kind of like, most people think it doesn't matter. So maybe you should form your answer right now and kind of think of what you should do. Switch, stay, doesn't matter. Most people will say, okay, you're down to two doors, so it doesn't matter, half half. It doesn't matter if you stay the same or not. But it actually does help you if you switch. You have a better chance of winning. So there's a lot of ways to show it. You can do a simulation. Below, I used a Bayes theorem argument on the next page. But I thought, well, first I'll show you a simulation. So here is a web page. You can probably see there's the address up there, but I'll just play a round of it for you. Actually, I have a speaker in. Here's how it goes. So you're the contestant. You're going to choose one of these doors. Let's choose door number 3. And then Monty Hall opens another door that you can see the prizes in there. You can actually, well, maybe you heard the pig there. So now your choice is stay with that door or switch. I'm going to switch. Yay, and you see I won the big prize. Let's try again. This time I'm going to choose number 2. He shows me 1. I'm going to switch again. And this time it wasn't good. I should have stayed, but okay. So far it looks like it doesn't matter. Let's try another time. I choose 1. He shows me 2, and I'm going to switch again. Yay! So far it looks like there's a 2/3 chance I win if I switch, and well, I don't know about this thing. I don't usually go by this down here, but let's try one more time. Choose 1. And go to 3. Okay, so this again is supposed to be random. It's not, they're not picking it, for you. But the idea is you have a 2/3 chance to win if you switch, and if you don't switch, you have a 1/3 chance of winning. So I would think you'd want to switch. And let me go back to that lecture again. I think the easiest way for me to show you is, consider the sample space. Here's door number 1, here's door number 2, here's door number 3. Here's what could happen. The winning door could be 1, and you could have 2 losing doors. The winning door, oops, let's do that again. The winning door could be 2, and then the winning door could be 3. Okay, but let's just assume, and it doesn't really matter, let's draw a line here. Let's assume you chose door number 1 to start. You can see in 2 of the 3 cases, you're gonna win if you end up switching to one of the doors 2 and 3. You know he's always going to open. In this case, he could open either one. In this case, he'll definitely open 3. In this case, he would definitely open 2. It's always going to benefit you to switch because you can see 2 of the three cases, if you switch, you're going to win. Another way I like to show people, imagine if we did this with, this isn't going to be perfect, but imagine if we played this game on and on and on and on and on. Let's have 10 doors. 1, 2, 3, all the way up to 10 doors. And imagine if I open, like say now you choose door number 1, and I open for you 2, I open 3, I open 10, and the only one I don't open, let's say right here, is number 7. Now, do you think you chose the winning door right off, or do you think it's behind 7? And remember, I'm showing you all the doors that, I don't know why that's not staying, but I'm showing you all the doors that don't have a prize. So does 7 have the prize, or were you lucky enough to choose the winning prize right off? And that would be 1/10 that you chose it originally, and there's a 9/10 chance it was behind one of these doors, because that last door kind of is sucking in all the probability that the other doors didn't have. I don't know why I can't write one. Okay, there it is. So it's kind of a cool problem. Anyway, the point is you should switch if you want to win. If you ever go on this game show and you can't phone a friend, just know that you should switch. Okay, let me turn this thing off.